The world did not realize it at the time, but long before American soldiers stormed beaches or flew into enemy skies, another kind of war had already begun. Quiet, invisible, and fought far from the front lines. It was a war of ideas. A war of engineers. A war of minds pushing steel, electricity, and imagination past every known limit. And in the year before America officially entered World War II, inside dusty laboratories, makeshift workshops, and forgotten factory corners, a small circle of American innovators were already working on breakthroughs that would one day turn the tide of the entire conflict. They were not generals. They were not famous. Many of them had never even seen a battlefield. But they felt something coming. They sensed the world tilting toward catastrophe. And they knew, if the United States was ever dragged into that global fire, the war would not be won by numbers alone. It would be won by the country that could outthink its enemy. America faced a terrifying truth. The Axis powers had prepared for years. Their armies were disciplined. Their weapons were refined. Their invasions were swift. But tucked inside this looming threat was an opportunity. If America could produce machines that no one had ever seen, if it could match its industrial might with bold engineering imagination, then the nation could change the course of history. So in 1940, in places the public never saw, teams of engineers began designing machines that seemed impossible. New ways to fight submarines. New ways to detect aircraft. New ways to mass-produce planes and tanks at speeds that defied logic. Some of these ideas would be rejected for being too ambitious. Others would be buried in dusty file cabinets for decades. But a few, just a few, would become the breakthroughs that helped crush the Axis war machine. One engineer later described the feeling as standing on the edge of a storm and racing the lightning. Every hour mattered. Every blueprint mattered. The world was falling apart overseas, and here at home, America had one chance to stay ahead of disaster, by reinventing the very tools of war. And as Europe burned, the first of these breakthroughs took shape in the hands of men and women who believed that innovation itself could be a weapon. Their work was secret. Their progress was fragile. But their determination carried a message. America would not just join the war. America would transform it. Their inventions were still unknown to the world, yet soon they would rewrite the fate of nations. Before America even fired a shot, one of its most important breakthroughs was unfolding inside a cramped room at the Massachusetts Institute of Technology. America needed a way to see what the human eye could not. The British had early radar, but it was fragile, inconsistent, and easily disrupted. The Axis had grown bold in the skies, confident in the element of surprise. America needed something stronger, something that could spot enemy aircraft before they rose above the horizon. That answer came from a group of engineers who believed that radio waves could be bent, shaped, and amplified into something the world had never imagined. They called their creation the cavity magnetron. To most Americans it meant nothing. But to the engineers at MIT's newly formed radiation laboratory, it meant possibility. This strange device was small enough to fit in the palm of a hand, but it could generate microwaves of immense power. With it, radar could suddenly become sharp, fast, and deadly accurate. Tracking a bomber formation in the dark would no longer be guesswork. Detecting a submarine periscope breaking the surface would no longer depend on luck. And so, in secret, America began building a radar network that stretched across coastlines, atop towers, and inside warships. The engineers worked day and night, their fingers stained with graphite and machine oil, their eyes burning from sleepless months. But they kept going. Because they knew the breakthrough was real, and they knew it was needed. In the years to come, this radar would become one of the most important American inventions of the war. It would guide pilots, defend convoys, and reveal the enemy long before he could strike. But in these early days, all of that existed only on blueprints and prototypes. Still, the engineers kept building, testing, failing, rebuilding. And somewhere in those long nights, they began to sense the truth. The invisible world was becoming visible. Radar would become America's eyes in the darkness. And darkness was one of the Axis powers' favorite weapons. America's next breakthrough was not a device, it was a method, a system. A way of thinking that took an impossible problem and solved it with assembly line precision. Before the war, building a plane required hundreds of hours, thousands of rivets, and the steady hands of seasoned craftsmen. But America didn't need hundreds of planes. It needed tens of thousands. Enter the engineers of Willow Run. When Ford Motor Company was asked to build a bomber capable of crushing the Axis war machine, they faced a task that bordered on madness. Transform a car manufacturer into the largest airplane factory in the world. Henry Ford believed in mass production. But producing a complex four-engine bomber was nothing like assembling a Model T. Still, the engineers refused to bow to doubt. They redesigned the bomber piece by piece, turning it into something that could be built in sections, moved down conveyor lines and completed by workers who had never touched an aircraft before. Willow Run became a miracle of steel and determination. At first it failed, often. But piece by piece, day by day the system worked. And then, one freezing morning, the factory achieved something no one had believed possible. A fully assembled B-24 Liberator bomber rolled out every 63 minutes. One plane. Every hour. This was not just industry. It was engineering at a scale the world had never imagined. Hitler reportedly refused to believe the production numbers. They seemed impossible. But in America, impossible was becoming routine. While factories roared, another breakthrough was unfolding in quiet rooms where engineers worked with pencils instead of machines. The Axis powers spoke in encrypted messages, webs of numbers, symbols, and mechanical pulses. To break them, America needed a new kind of mind. The engineers at Bell Labs answered the call. They believed that communication could be intercepted, analyzed, and decoded through machines faster than any human could dream of. Their early work gave birth to electromechanical computers capable of sorting patterns at speeds no enemy cryptographer imagined possible. But more than speed, America needed something deeper: the ability to hear meaning inside noise. The codebreakers built circuits that recognized repeated rhythms, filters that separated signal from the chaos, and devices that could read enemy intentions before they were acted on. In time, their machines helped expose submarine positions, troop movements, and hidden strategies across two oceans. These early computers were not beautiful. They were not elegant. They were loud, bulky, temperamental creatures of wire and steel. But they worked. And in a war where information meant survival, America's quiet engineers gave the Allies something priceless: foresight. When American troops first faced German armor in North Africa, they realized something terrifying. The enemy tanks were faster, stronger, and deadlier. The engineers back home received the message in blunt military dispatches: American armor needed a miracle. So they began designing machines that could withstand the harshest battlefield on Earth. The M4 Sherman was not perfect. Soldiers knew its weaknesses well. But what the engineers created was something Germany never expected: a tank that could be repaired anywhere, built anywhere, and modified endlessly. This adaptability became its greatest weapon. Engineers designed new tracks for desert sand, new armor for ambushes, new turrets for new guns, new filters for dust storms. The Sherman evolved again and again, becoming a machine that could be mass-produced and rapidly improved at the same time. American tank design was not about superiority, it was about flexibility. About building a machine that could be fixed in the field with anything from factory parts to scrap metal and ingenuity. And that adaptability allowed American armored divisions to keep advancing, even when the odds should have stopped them cold. The Atlantic Ocean had become a graveyard of steel. Germany's U-boats prowled the waves with deadly precision, cutting off supply routes and threatening to starve Britain into surrender. But American engineers were already working on the weapon that would change the ocean war. It was called ADF sonar, a system that could read underwater reflections with extraordinary accuracy. Engineers turned the ocean into a map of echoes, allowing destroyers to pinpoint submarines long before they reached striking distance. But sonar alone wasn't enough. Engineers needed a weapon to match it. So they created the Hedgehog, a forward-firing system that launched dozens of small explosives that detonated only upon contact. For the first time, Allied ships didn't need to guess a submarine's position. They could strike with precision. U-boat commanders soon realized the terrifying truth: the hunters had become the hunted. While the world focused on battles, engineers focused on something less glamorous, but far more decisive: movement. Warfare had changed. Armies needed fuel, ammunition, spare parts, food, and medicine delivered with impossible speed. No matter how strong the tanks or planes were, they were useless without supplies. So America built its most overlooked breakthrough: the world's first military logistics machine. Engineers designed portable pipelines, collapsible fuel tanks, mobile repair shops, and prefabricated docks that could be assembled on foreign shores in days. They created trucks that could operate in mud, snow, and jungle. They built standardized crates that allowed cargo to be moved twice as fast. And the piece de resistance was the Liberty ship, designed, engineered, and built to be replaced faster than the enemy could sink them. This was engineering disguised as organization, innovation disguised as planning. And it allowed the U.S. military to supply two full-scale wars at opposite ends of the globe. In the early days of the war, American pilots realized they had a problem. Their planes were durable, but their weapons were outdated. Dogfights demanded something faster, steadier, and more lethal than existing mountings could deliver. So engineers stepped in and redesigned aircraft gun systems from the inside out. They created synchronized firing mechanisms that allowed guns to fire through propellers without striking them. They developed new high-velocity rounds that tore through enemy armor. They designed wing mounts capable of supporting heavier firepower without destabilizing the aircraft. But their greatest triumph came with fire control innovations. Small devices that calculated lead angles, airspeed, and enemy movement in real time. For pilots, it was like suddenly being able to see the future. Planes that once struggled in tight engagements now dominated the skies. And as American air power grew sharper, faster, and deadlier, the engineers understood something profound. The war in the air would be won by those who could calculate the impossible. Warfront after warfront revealed a brutal truth. The fastest armies were stopped cold by rivers. Germany had mastered the art of using blown bridges to stall the Allies. Every destroyed crossing bought them precious time to reorganize, retreat, or counterattack. American generals knew that without a breakthrough in rapid bridge engineering, the advance across Europe would slow to a crawl. So engineers back home designed something extraordinary: portable, modular combat bridges that could be deployed under fire, in darkness, or in the worst weather Europe could throw at them. These were not just planks and steel beams. They were feats of precision engineering, light enough for soldiers to carry, strong enough to support tanks, and simple enough to assemble with minimal tools. The Bailey Bridge became America's unsung hero, a structure so brilliant in its design that it could hold staggering weight with no heavy equipment. Soldiers learned to build them in hours, sometimes minutes, hammering steel beams into place while artillery exploded around them. Each build felt like a race against time, a contest between engineering and destruction. When American forces approached the German border, they found the enemy had destroyed nearly every significant bridge. Rivers became defensive lines, natural walls that threatened to halt the Allied push into the heart of the Reich. But every time a bridge lay in ruins, American engineers stepped forward. They trudged into icy water with ropes tied around their waists, tested currents, measured distances, and calculated load-bearing limits on the spot. Some of these men had studied engineering in quiet classrooms. Now they planned structures while shells burst overhead. Engineers learned to build in darkness, their hands guided by memory and instinct. They assembled pontoon bridges while snipers watched from tree leans. They anchored floating sections while currents dragged at their legs. They rebuilt steel bridges piece by piece, welding sparks flicking like fireflies in the night. And every time a tank rumbled across a newly placed span, it meant another breakthrough, another advance deeper into enemy territory. To soldiers on the front lines, these bridges were miracles. They symbolized movement, momentum, and the unstoppable force of an army that refused to be slowed by terrain or sabotage. Entire armored divisions crossed rivers that German commanders assumed were impassable. Entire towns were liberated because engineers had mastered the craft of turning water into pathways. Even generals quietly admitted that without these innovations, the advance across Europe might have taken years. By the war's end, American bridge engineers had built more than 2,000 major combat bridges. Their creations were temporary by design, but their impact was permanent. They reshaped the battlefield, defied the limitations of geography, and proved that ingenuity could defeat even the strongest natural barriers. With every river crossed, the engineers knew they were helping carve the path that would lead the world out of darkness. If war was a machine, fuel was its blood. Every tank, truck, aircraft, and landing craft depended on it. Yet transporting fuel across oceans, beaches, and continents was one of the most dangerous tasks of the war. Enemy planes targeted tankers. Submarines stalked convoys. Even when fuel arrived safely, it often had to be moved by hand, drum by drum, across muddy terrain where vehicles could not reach. America needed a breakthrough, something that could feed an entire army with fluid speed. Engineers answered with a bold solution: portable pipelines built from lightweight metal and flexible hose, capable of stretching for miles across hostile ground. They created systems that could be assembled in hours, snaking across fields, forests, and bombed-out towns. These pipelines delivered fuel directly to the front lines, bypassing roads choked with traffic and reducing exposure to enemy attacks. For the first time, an advancing army could outrun its own logistics, and still be supplied. But the pipelines were only half the story. Offshore, American and British engineers collaborated on an even more audacious creation: underwater fuel lines laid across the English Channel for the D-Day invasion. These lines, known as Pluto, Pipeline Under the Ocean, carried fuel from Britain directly to Allied forces on the European mainland. The engineering challenges were staggering: strong currents, unstable seabeds, and harsh coastal conditions. Yet the pipelines held, delivering millions of gallons of fuel and powering the liberation of France. On land, mobile fuel depots sprang up behind the advancing front. Engineers designed collapsible storage tanks that could be deployed within minutes. They created pump stations that ran on portable generators. They crafted filtration systems to keep fuel pure despite dust, mud, and battlefield debris. Every problem, every terrain challenge, every logistical barrier, was answered with a new piece of engineering brilliance. Fuel flowed like a river, feeding the engines of victory. Soldiers often never saw the pipeline crews. They worked behind the scenes, moving under cover of night, laying hose across ravines, weaving lines through rubble, and repairing leaks under sniper fire. Their work lacked glamour, but without them, armored divisions would have stalled, aircraft would have stayed grounded, and infantry units would have been stranded far from support. They kept the war alive with every gallon pumped forward. By the time the Allies reached Germany, the pipelines had stretched hundreds of miles. They crossed rivers, climbed hills, and threaded through shattered towns. It was a system born of urgency and executed with genius. And when victory finally came, many commanders acknowledged a truth few civilians ever learned. The war was won not only with bullets and bombs, but with the quiet, relentless pulse of fuel flowing through invisible veins of steel and rubber. In every war, machines break. Tanks throw tracks. Trucks crack axles. Guns jam. Aircraft return riddled with holes. Before the American engineering revolution, repairing battlefield equipment required sending it miles, sometimes hundreds of miles, back to major depots. It was slow, expensive, and often impossible during rapid advances. America needed a new approach: repairs that could travel with the battlefield. So engineers built mobile repair workshops, rolling factories packed with welders, lathes, spare parts, compressors, and skilled technicians. These workshops followed the armies wherever they went, sometimes creeping just a few miles behind the front line. When a tank broke down, it no longer needed to be abandoned. Mechanics brought the workshop to the tank. They patched armor in muddy fields, replaced engines in orchards, and repaired transmissions beside smoking craters. Some workshops were simple trucks. Others were elaborate trains, each car serving a unique purpose. Machine shops, tool depots, blacksmith rooms, even small forges. Engineers designed modular kits that allowed crews to fabricate replacement parts on the spot, even ones that had never existed before. If a tank needed a new bracket, a new armor plate, or a custom machine part, they could build it in the field. It was mechanical improvisation elevated to an art form. Aircraft received similar treatment. Mobile aviation repair units deployed near makeshift runways, where crews worked day and night patching wings, replacing engines, and sealing bullet holes. Some planes returned to the sky within hours of being shot up. Pilots marveled at how fast their machines were restored, sometimes faster than they believed possible. The workshops made American air power relentless. What should have grounded entire squadrons only slowed them down momentarily. The Germans were stunned by this capability. Their own repair system relied on centralized depots and factory returns, leaving disabled machines to rust on battlefields. But American forces refused to leave anything behind. Engineers treated every disabled tank or wrecked truck as a puzzle waiting to be solved. They dragged them out of shell holes, hauled them from rivers, and salvaged usable parts even from burnt hulks. They turned scrap into strength, waste into opportunity. By keeping machines alive, mobile workshops kept the offensive alive. Every bridge crossed, every town liberated, every breakthrough achieved owed something to these engineers who lived in grease-stained uniforms and worked by the glow of welding torches. They made sure that America's war machine never ran out of breath. And in doing so, they helped ensure that the Allied advance never stopped. Not for a day, not for an hour, not even when the front lines shifted faster than supply maps could keep up. Europe was a continent of roads, bridges, and rail networks. The Pacific was something else entirely, a vast ocean dotted with islands, jungles, mountains, and coral reefs. The terrain was unforgiving. The distances were enormous. Every invasion required landing on remote beaches, carving paths through wilderness, and building functional bases within days. The U.S. military needed more than engineering. It needed creation, the ability to conjure infrastructure out of thin air. The Seabees, the Navy's construction battalions, became the answer. Made up of engineers, carpenters, electricians, and skilled tradesmen, they were trained to fight and build at the same time. They stormed beaches alongside Marines, bulldozers roaring behind them, ready to clear jungles, fill swamps, and lay down airstrips under enemy fire. They turned raw, hostile terrain into launch pads for the next stage of the war. In the Pacific, every island became a new engineering challenge, and a new opportunity. The Seabees built airfields out of crushed coral, creating runways where nature had never intended flight. They carved harbors with dynamite, anchoring docks where days before only surf existed. They erected barracks, hospitals, fuel depots, and command centers in record time. Their speed was astonishing. On some islands they built airstrips in just 48 hours, airstrips that could host bombers the size of small buildings. Their engineering extended beyond construction. They built the roads that carried supplies inland. They installed water purification systems. They assembled radar stations on ridgelines and carved defensive bunkers into cliffs. Every structure, every trench, every landing zone expanded American reach across the Pacific. The enemy often expected a long delay between invasion and infrastructure. Instead, they watched in disbelief as entire functional bases appeared almost overnight. But the work came at a cost. The Pacific climate was brutal: heat that drained energy, rain that washed away progress, and diseases that stalked through camps. Coral dust cut into skin and lungs. Mosquitoes spread infection. Jungle terrain swallowed machines whole. And always there was the threat of enemy attack: shells falling as crews operated cranes, bullets snapping through palm leaves as bulldozers pushed forward. The Seabees kept building even when the ground itself seemed to resist them. By the end of the war, the Pacific had been transformed from an uncharted expanse into a chain of Allied strongholds. Each one was built by engineers who refused to be limited by distance, terrain, or danger. Their work turned islands into stepping stones and stepping stones into pathways. Pathways that led American forces slowly, steadily, unrelentingly toward Japan. And with every airstrip completed, every harbor opened, every beach fortified, the engineers understood their purpose. They were reshaping the Pacific so the war could end. America's war machine did not succeed on raw power alone. It succeeded because thousands of small engineering breakthroughs quietly reshaped what the word precision meant. Before the war, most heavy machinery was crafted through slow and deliberate machining, one part at a time, in workshops where a single skilled machinist controlled every cut. But wartime demand shattered that model. Factories now needed to produce aircraft components, tank gears, and artillery shells with microscopic tolerances, and they needed to do it not hundreds of times but millions. Engineers, machinists, and metallurgists turned to new measurement tools, like the Johansen gauge blocks adapted from Sweden, and pushed their accuracy to limits never attempted. America began building machines that could create identical parts across thousands of miles. A revolution that would quietly underpin every battlefield success to come. This precision revolution became most visible in aircraft production. Engines like the Wright R2600 or Pratt & Whitney R2800 required crankshafts and cylinder heads machined to tolerances of thousandths of an inch. A single deviation could spell catastrophic failure. Engineers built rigid new jigs and fixtures that locked components in perfect alignment, eliminating the subtle human errors that once plagued mass production. Even more revolutionary was the use of air gauges, which used streams of low-pressure air to measure the dimensions of a part with incredible sensitivity. These tools allowed factories to inspect thousands of parts per shift with unmatched speed, creating a consistency the Axis simply could not replicate. In Detroit, the automobile world brought its own genius. Men and women who once machined car engines now applied their expertise to tank transmissions and aircraft starters. Ford engineers redesigned entire workflows so that parts arrived in exactly the right sequence, eliminating downtime and ensuring that the machines that made the machines ran around the clock. Packard's mastery of precision tooling allowed America to mass-produce the Rolls-Royce Merlin engine under license. Engines so reliable they powered the P-51 Mustang into legend. These companies didn't just build engines, they redefined how engines could be built. Precision also transformed artillery. American engineers improved the manufacture of rifled barrels, creating smoother bores that resisted wear and maintained accuracy over prolonged firing. Shell casings, once prone to microscopic imperfections, were now produced with near-perfect uniformity. The consistency of American 105mm shells became a silent battlefield advantage. Each round behaved predictably, each trajectory reliable, each shot an expression of a national engineering system that worshipped accuracy. Even small arms benefited. The famous M1 Garand, which required dozens of precisely milled components, became a symbol of American manufacturing excellence. Factories introduced new broaching tools, new grinders, and new heat treatment cycles to maintain uniformity. Soldiers knew the rifle in their hands was built with the same exacting standards as millions of others. It fired true because a nation of engineers had obsessed over the inches and fractions that turned metal into reliability. This quiet revolution did not make headlines. It lacked the drama of battles, the thunder of artillery, or the roar of bombers. But it was everywhere. In every tank that started on a frozen morning in the Ardennes, in every engine that carried bombers across the Pacific, in every rifle that answered a desperate call in a muddy foxhole. America won not just because it produced more, but because it produced better, with a level of precision that transformed the very meaning of industrial war. As the skies turned into the defining arena of World War II, American engineers confronted a brutal truth. Survival at altitude demanded innovation. Aircraft were being torn apart by enemy fire, by violent winds, and by the unforgiving physics of flight. Engineers realized early that better engines and better guns were not enough. Aircraft needed to be stronger, safer, more resilient, even when riddled with bullets. The answer came through a series of engineering breakthroughs that would fundamentally change aviation. One of the most important innovations was self-sealing fuel tanks. Early in the war, a single bullet puncture could transform an aircraft into a fireball. Engineers developed a layered rubber and fiber system that absorbed fuel, swelled on contact, and sealed punctures even after violent hits. The result was astonishing. Planes that once fell from the sky now limped home with fuel tanks peppered by enemy fire, their survival owed to a material born not from glamour but from quiet experimentation in rubber labs scattered across America. Armor innovation followed a similar path. Engineers studied the patterns of enemy fire, mapping bullet impacts to identify precisely where armor mattered most. Instead of reinforcing entire airframes, they added carefully contoured plates around the cockpit, engine block, and vital hydraulics. This selective armor reduced weight while dramatically improving crew survival. In bombers like the B-17, pilots returned from missions with armor that bore silent witness, holes, dents, and gouges that would otherwise have been fatal. Engineers also solved the problem of high-altitude flight. Air at 25,000 feet was thin, brutal, and deadly. American scientists at Wright Field developed turbosuperchargers capable of compressing thin air and feeding engines the oxygen they needed to maintain power. Planes like the P-47 Thunderbolt could now climb, fight, and dive with unmatched ferocity. Their engines rarely lost power in the upper atmosphere, a transformation that gave American airmen a confidence no Axis pilot could match. Another breakthrough was structural redundancy. Instead of relying on single cables or single hydraulic lines, engineers built aircraft with multiple backup systems. If a cable snapped, another carried the load. If a hydraulic system was punctured, a secondary system took over. This changed everything. Aircraft no longer disintegrated when damaged. They fought back, wounded but unbroken. Stories of bombers returning with half a wing missing weren't miracles, they were engineering triumphs. The final innovation was the shift to all-metal airframes built with stress skin construction. Riveted aluminum, shaped into aerodynamic curves, formed both the surface and the strength of the aircraft. This eliminated the drag and fragility of older designs. The planes became faster, tougher, and more fuel-efficient. This design philosophy would dominate aviation for decades, but in the 1940s it was nothing short of revolutionary. Together, these breakthroughs made American aircraft some of the hardest to destroy in the world. They weren't invincible, no machine is. But they endured punishment that should have ended them. They brought crews home when hope seemed impossible. And they did so because engineers, far from the battlefield, imagined ways to cheat death with rubber, metal, mathematics, and an unshakable belief that survival could be engineered.